Okay, off we go. Making green choices. What I talked about this morning was some of the analysis techniques that we've applied against the engineering to make the neighborhoods work and to make what was handed to us work. Because typically the drainage engineers are the last people into a site, and we're asked to fix everything that the planners did, everything that the lawmakers did, everything that the developers did, and we're the last people to come in and they say, fix it for us. You've been talking about integrating a process, and guess what? That's what I want to talk about too. But as we go through, the thing that's important is our knowledge is increasing. We're learning more and more, and the processes and the interconnections of the environment to the engineering, to the neighborhoods, to the whole built form and function of the community. What we have an opportunity to do now, because people are asking for it, is to change our guiding framework, to look at how can we improve the processes, what can we put in place to move ahead. And we have the ability now to do that with some pretty good tools with a lot of scientific basis behind them, rather than trying to pluck targets out of the air with no scientific foundation. And as we're going along, our learning is continuous. We keep refining what we know, and we have to keep adapting. And you've seen this over the last few years that we've had a tremendous change in people's attitudes and approaches. So we are learning and we are adapting. And right now, I'll say we don't have the final answer, because next year we'll know something else. I don't know what that's going to be, but we will know something else. So what I want to talk about is how can we get some of this planning and integration going. I'm going to toss in a bit of engineering, but hopefully not very much, because I know your eyes glaze over and roll back if I throw up another graph. And I'm going to show a few shots of screen captures of water balance model in action, but I'm not going to go into it because it's just a tool, and we're talking about the process. Now, in terms of the planning, I've heard a lot of people talk about what's the watershed look like, what's the vision, what do you want it to look like, how do you want it to be livable, do you want green space, do you want it all built up, what do you want? Well, this matters to me as somebody looking after the drainage, because it affects what I can do, what I have to do, and the cost at the end of the day. It affects the developers because it affects what they can do, their cash flows. It affects everything. So the watershed vision is tremendously important. When we were doing the Fergus Creek watershed, I threw out the concept that maybe we needed a vision for the watershed because it really affected things. One of the things I did was I went through some examples in the city of some of the developments, and I asked, is this what you want to see in Fergus Creek from throughout the whole watershed? And this is up in East Clayton. It's 8 units per acre, 8 real units per acre, not a zoning number, but 8 real units per acre, with 60% imperviousness. And if you look at it on the ground, this is what it looks like on the ground. And the thing that strikes me is some of the boulevards are getting pretty skinny, and some of the trees, if you look at it, I'm not sure how you're going to get some big trees out of this. So I'm not convinced we're going to see trees with the canopies touching over the streets. And I'm saying that because of my background other than being an engineer. We looked at other developments. These are as a multifamily site. Townhouse is 14 units per acre. And if you look at it, it's 75% impervious. Here's my bias again. I don't personally like this kind, but a lot of people live in these things. And if you look at it on the ground, So again, I asked the planning people, is this what you want to see from in the whole? Anyway, so you can see that each of those developments, each of those housing types would really impact how the drainage works, how the stormwater management works, how the rainwater balance operates, what kind of infrastructure we'd actually have to construct to mitigate the impacts. So from my view, the vision of the watershed is absolutely critical to my side of the work in planning of the drainage. If I don't have a clear vision, then I have to assume the worst, and then I have to jack up essentially push the price of the infrastructure up, because that's what I have to do to have some assurance that things will work. But if we start integrating the planning process early on, as Surrey is doing now with the integrated stormwater management plans that feed into the neighborhood plans, what we have is an opportunity to create multi-purpose, multifunction facilities. Facilities that do both the engineering and shared parks, have some possibility of having multiple sources of funding. So imagine having a park you can use for drainage and have both parks and engineering paid for it, rather than having a park and an engineering pond or something. So it starts to provide some synergies. Now, Surrey is going down that road, and I applaud their progressiveness. It's just there's an opportunity for other people to learn. So, from the engineering, the question is what's important and what's different in this process? Well, what's important for the engineering is rates of flow when we get down into the drainage. It's not just 1 or 2 flows or a 5-year or a 100-year discharges. It's all the flows, the full range of discharges. And really what's critical is the duration of flow, because we can't, in spite of what some people say, we can't match the hydrographs of individual storms. That's just not going to happen. So what we can do is start getting closer to the total duration. We can start looking at the minimum flows, and we can look at the effects on the streams, so the morphology and erosion. Typical year, there's a lot of information in this chart. First is the two storm events. The one early in the year, this is a 1 year 1997 simulation. Early on in the year, we have a small relative rainfall event. And the rainfall is represented in these are daily rainfall and daily runoff. And the rainfall is represented from the top down. And so the event on the left is about 11 millimeters per day. And that resulted in about a 2-year term period discharge. The second event, off into September, is about 16 millimeters. It's tough to see the storm event. So the lesson here is that rainfall doesn't equal runoff. There's no direct one-to-one relationship, because there's a whole bunch of processes built into it, and you can't just design for a storm event.
And Jim, this image is in your copies of the commentary on page 4.
The second thing that's important is that when you add up all the volume of runoff, the 90% of the volume is in a very small discharge rate. And we could, in fact, take 90% of the volume off and store it away, do something with it so that it doesn't get into the stream. But you're not going to affect the peak discharges in the stream. And you're not going to reduce the number of times those happen. So if we use a 90% capture, we could nicely do that and still have zero mitigation effect on the stream. So here's again an example of the 90% rule. It was a good start, but we've learned that that's not enough.